All right. So good morning, everyone. I'm really happy and thrilled to be here today. The title for my keynote talk, I've tried to keep it in keeping with current research trends. So I'm going to talk about harnessing large language models as research assistants and in science. And specifically, I'll be presenting some of the research work that we've been doing in my group. So first of all, a word of acknowledgement. All right. So yes, I'm really happy to be here at Leuphana University, if I got it right. Yes. Thank you for hosting this great event. I would also like to acknowledge the NFBI for Data Science Initiative that is also responsible for this event. And special thanks to Ricardo for this very generous invitation. And to his team, of course, for organizing this day and making all of this possible for us. So with that, I'm going to get started. So at the beginning of my talk, I'm going to try to establish some common ground by briefly introducing the Open Research Knowledge Graph project. So essentially, the Open Research Knowledge Graph is one of the services that we are developing as part of the NFDI for Data Science initiative. What it is a digital library for machine actionable knowledge communicated in scholarly literature. And here specifically, the aim is to capture structured scholarly knowledge of content beyond keywords, so not just bibliographic metadata. So on this slide, basically, you see a juxtaposed view of scholarly communication. On the left side of the screen, you see a traditional research article. On the right side of the screen, you see a structured representation of the contribution of that article in the Open Research Knowledge Graph. So we have several objectives with this project. So to provide an overview of the state of the art for research problems, tackle interdisciplinary challenges such as climate change research, disease prevention, and so on, and also focus on having scientific content within structured representation and fair data. So finally, to bring scholarly communication in a sense to the 21st century. So so in the next slides, I will be showing you two use cases where we've modeled contributions from representing different research problems in the ORKG. So the first one was the SARS-CoV-2 basic reproduction number. So this was something that we did in during the pandemic. So we kind of tried to represent the contributions around this one parameter. And the parameter was the basic reproduction number, which tells you how fast the disease spreads through a population. So in order to have a structured representation in the ORKG, we needed to identify the salient properties of this particular contribution. So here we see, okay, it's the basic reproduction number itself, then the location where the study was conducted, because this number is contingent on the population studied, and the duration when the study was conducted. So it changes, with time. So with this basic knowledge, we then have the structured representation of the contribution in the ORKG. And when we do this for multiple such papers on studying different populations, we can then have this structured comparison of sorts across different contributions, which makes it easier to track the state of the art on this particular problem. Right, so this is currently not possible, obviously, by the current predominant method of scholarly communication that are hardly machine actionable. Another use case then is repetitive transcranial magnetic stimulation studies. So we kind of represented the salient properties around this research problem within the ORKG for different studies that were published over time, and then published a large-scale comparison. So this is to say that this approach scales or maps across domains in science and is not specific to any given domain. So, of course, it's a scholarly knowledge publishing platform, and therefore it's supported by an entire workflow that supports structured knowledge publishing. So we have templates, you can publish visualizations over data within the knowledge graph, you can publish comparisons, structured papers, as well as machine actionable reviews that basically combine several such comparisons in a single article. So this now, with this brief introduction of the Open Research Knowledge Graph, I'm going to shift to the main focus of this talk today by talking about some of the work that we've been doing in my research group, which is called SciNext. And the focus of the work in our research group, or at the heart of the objectives of the research group, is to develop AI services that can power scientific knowledge graphs, and specifically knowledge graphs like the Open Research Knowledge Graph. So we have an aim, which is to have an optimal mix of AI neural and symbolic approaches to automatically mine articles' contributions in a structured manner to augment and scale the Open Research Knowledge Graph. And this entails several different kinds of modules. So first of all, we need the structured knowledge annotated. Secondly, we need to implement the AI learners to automatically then annotate new incoming articles for the same objectives. And finally, we also need mechanisms to evaluate the quality of the graph. So this is all contained within the umbrella of the research project, or defined within the umbrella of the research project. So a bit of a motivation for why we need AI services, of course, time to scale. With AI, we can basically scale the knowledge graph much faster than if it was just done by domain experts. Secondly, given this large-scale structured information, it allows us to leverage next-generation information technology solutions such as dashboards to allow researchers smart filtering options over scholarly articles. So that's another motivation of this project. So this talk is planned as a reflection on some of our research, and this is basically also presented as published articles in various conferences over time. So in this talk, I will focus on 5 works that we've done, addressing different themes around harnessing large language models as research assistants or in science. So the plan for the talk is a walkthrough of various applications of LLMs for science. I will start out with discussing our work on developing a research assistant, then move on to discussing our AI-powered virology dashboard. Then I will shift the focus to then talking about how we've tested LLMs for various tasks around developing ontologies, which are also central within scientific knowledge graphs. And then I will talk about how we've also applied LLMs as evaluators themselves for a different task. So let's get started with our research assistant. So the objective here was that we noticed that many of us use conversational AI agents like ChatGPT and Gemini already for various of our tasks. So we tried to figure out how could we streamline this process of like harnessing these conversational AI agents for various tasks within research. So we kind of like formulated and defined those specific tasks, and then we kind of streamlined them as prompts, which were then fed to the user as like placeholders that were taken as input. So specifically, what I mean by that is that we defined a tool that comprised specific scenarios where these conversational AI agents can be used to assist researchers. So here we defined 2 different classes of objectives. One was primary objectives, and the second was secondary objectives. So now when we think about research assistants, that could be like a very broad topic. That could mean just basically so subjectively anything to any specific researcher. So what we essentially focused on within the primary objectives was to obtain these fair research comparisons for powering the ORKG and other such knowledge graphs. So that around this scenario, we defined our primary objectives, and our secondary objectives were then addressing tasks like generating blog posts, research ideas, writing assistance, and so on. So how did we come up with these objectives? As I said, our primary objectives are mainly focused on trying to generate these fair research comparisons. So for that, we have the ORKG as an inspiration. And so first of all, we looked at one feature within the ORKG, which is the papers. So now we look at ORKG papers and what can AI help us with in terms of having the structured information about papers. So first of all, they could recommend these salient properties of research. Secondly, they could also automatically extract these findings from given a paper or from their own knowledge. So these were two scenarios that we said, okay, this is where AI can help us with. Now we need to define a prompt around these scenarios. So here we kind of have one usage where we say, okay, we want to get recommendations for salient properties. And here the assumption is that the user knows the research problem in advance. And the research problem is also so well known that ChatGPT can be expected to offer suggestions from its own knowledge. So no context given. So it's just given a research problem and set to suggest salient properties. So here is how we kind of like define the prompt. And then we left in a placeholder where specific research problems can be introduced. And so you see on the left here suggested properties from ChatGPT, and on the right ORKG model properties. And when we scroll through these properties, you can basically see a large overlap between what ChatGPT has suggested without any given context with those modeled by human experts. Essentially, of course, we have these suggested properties, and then you see that some properties are in addition and were not modeled by the human expert. So what this means is, yes, there are suggested properties, but this would take the step of then analyzing and distilling the suggested properties to an optimal model as reflected by the ORKG model properties. So this is kind of like a user action. Nevertheless, this is one way of getting started with structuring contributions in the ORKG using the help of LLMs. So as an aside, I actually wanted to reference this research article that we recently published, where we actually did a systematic study of various disciplines, and we kind of like curated ORKG structured contributions across these disciplines and prompted different large language models to generate properties, and then we evaluated how well or how the model compared with the human annotated properties. So that basic study is also released recently in this journal article. Okay, so going back to the research assistant, so we have a second usage scenario now, which is get recommendations for salient properties based on provided context. So here the assumption is the user knows the research problem in advance, but he also knows the context on which the large language model has to work. So it could be the title and abstract, it could be maybe the results section of the paper, and so on. So we have two placeholders here, one for the research problem and another for the context. So that's essentially the usage scenario, and a second objective now. So here we are trying to identify all of these research assistant scenarios. So we are trying to do it step by step. So secondly, we notice another feature in the ORKG, which is comparisons. So first, with the first scenario, we were just addressing one paper at a time. So now we address comparisons. So here again, we define certain usage scenarios. So the user knows the research problem and theme in advance, and they also know the entities to compare. So again, we are not giving much context apart from the entities. So as you can see, the COVID-19 basic reproduction number, and we've given entities like different locations where this can be studied, where the study has been conducted or might have been conducted to compare this value against. Similarly, for large language models, here we are given two entities, T5 and GPT-3. So that's basically what we are providing. And again, you can extend this scenario to getting comparisons based on provided context, which is kind of similar to the previous one. So now we come to the actual tool. So this is what the interface of the tool looks like. As you can see, the dark colored boxes are the active scenarios, and the light colored boxes are those that depend on one or more of these boxes having been completed to be activated. So there are certain continuation scenarios that are contingent on a step being completed. As we saw, there were primary and secondary objectives. So some of these scenarios are dependent on other scenarios being completed first. So our tool is essentially a React application, which acts as a bridge between conversational AI agents and next generation digital libraries within the primary objective. And it facilitates generating data for these libraries using either ChatGPT, Gemini, or what have you, conversational AI agents that are out there. And it assists end users to access relevant AI-generated data to address different kinds of tasks in research as part of the secondary objectives. So now this is another kind of a way of like scoping the field. So we asked ChatGPT, okay, what is research assistance? And then it tells us, yes, there is literature review, there is data collection and analysis, there's writing and editing, and so on and so forth. So we kind of like, in order to define the secondary scenario, we also kind of like had to like feed into or tune ourselves into some of these suggested points and see how we could model them within the research assistant. So focusing on the primary task to begin with, so we want to generate fair research comparisons. So here, the first step is we obtain salient properties for a research problem, and certain other functionalities exist is also refining definitions of salient properties based on the provided context. So that's also engineered within the tool, because now we want to sort of like, in the end, import this comparison within the ORKG or to another knowledge graph. And in this case, definitions of properties or definitions of resources are also essential to be contained within the knowledge graph. So of course, after this first step, there are several continuation steps where entities are compared for a research problem, contexts are compared, and so on and so forth. And then this slide basically lists the secondary task that the research assistant does. So it helps with brainstorming research ideas. So we've kind of like engineered a prompt with a few placeholders that can be simply harnessed to like get research ideas based on a research problem and so on and so forth. And this is divided into two scenarios. One is get research ideas. Another one is obtain user stories and criteria based on a context. So this is often very beneficial for projects and for companies and so on. Also writing basic grant applications. So we've kind of defined certain essential structural elements of a grant application. And so we just prompt the large language model to do that, and so on and so forth. So here is the workflow that it entails, at least for one of its scenarios. So the researcher comes in with a research question. They also have selected a certain context. So they interact with the tools, say they choose a research task, for example, generate a research comparison. So then they input the research question and context within the input fields, which is then templatized. And that can be copied into the large language model. Essentially, as a second step, the tool works as an editor. So the researcher can copy that table back into the tool and edit or curate those properties, change the values if they're wrong. And finally, they get a CSV file, which they can then import directly into the ORKG. So that's essentially the workflow. Looking a bit closely, so obtain salient properties for research. How would it work? So first of all, we select the button, get research dimensions for a research problem. So then we get prompted for input fields. So here, this is entered as GPT family of large language models. And then we click on generate prompt, which is then pasted into ChatGPT, which then, as you can see, generates a list of research dimensions with their descriptions. So it alleviates a great deal some of the tedium associated with representing knowledge in a knowledge graph, because it generates these descriptions for the properties already. So then the researcher just has to curate that information. So of course, once you have this copied back into the prompt, you could of course edit the descriptions and so on and so forth. So as a second step, a continuation step, now we want to compare context based on these suggested salient properties. So we select the scenario that has been activated, and then the researcher chooses to select maybe 4 properties, and then they provide a context within the context box and generate prompt. Now you can see that the large language model has basically structured the values for the contribution as well as provided research dimension descriptions, which can be then copied back, and then you can export it after editing it and fixing any errors and so on. You can then export this as a CSV file and import it into the ORKG or other knowledge graph systems. So it also helps with generating blog posts. So say you have some of these salient dimensions, and then you wanted to sort of discuss this like in a citizen science article, like a blog post. So you could actually select these dimensions and note that their definitions also sits under them. So that also informs what goes into like the content that the blog post is generated based off of. So that's basically some of the templated prompt with placeholders for the input that have come from the tool itself. So we've in this work, we basically tested the tool on different research problems, 3 different research problems to be specific, and they're also released online, so you could actually visit it and see how different responses have been generated from the tool. The code itself is publicly available, and it's highly customizable and modularly implemented, so anybody can play around with it and change any of these assistant scenarios or modify them. So basically, as a conclusion, many see AI conversational agents as tools to assist with work, not replace it. So already adopting them as digital secretaries or assistants. So playing into this familiar setting, we engineered the RA underlying each task are a set of customized prompts that assist end users to access relevant AI-generated data that addresses the research task. Thus, it standardizes the performance of a diverse spectrum of research tasks in a single tool via a modular and completely transparent workflow. So that is about the research assistant. So now let's move on to the virology dashboard. So at the very beginning of the talk, I presented the R0 estimates use case that we modeled as structured contributions within the ORKG. So those were human expert curated. So it's basically a team of human experts sat together and selected 30 papers and then defined their structured contribution in the ORKG. So what we wanted to do in this very early work was to kind of like leverage large language models to automatically structure this data and then define a workflow that, continuously fed the structured information into the open research knowledge graph. So what we did was we indeed fine-tuned a large language model to automatically extract the structured knowledge for new incoming papers. Furthermore, we implemented dashboards to allow researchers to kind of access scholarly articles in a more efficient way. And we will see that later, which is also implemented as a web interface. So indeed, to start out with, first of all, to define the problem, we needed a semantic model. So which properties are we going to use to extract the information for? So this came from the ORKG comparison that was a human expert created. And we identified 6 properties. So the disease name, location, date, the R0 value, the percentage confidence interval, and the method to compute the R0 value. Then we went ahead and annotated a large data set. So this was roughly 1,500 papers from the Cohort 19 corpus. One thing I need to mention is that the original R0 estimate comparison was created only for COVID-19, of course, but with this objective, we kind of wanted to generalize to all infectious diseases and not just COVID-19. So now this data set included papers that reported R0 estimates and those that may have mentioned R0 estimates but did not report it. So we basically use these signals to fine-tune the large language models to even filter out papers that were not reporting R0 estimates. This annotated data set is publicly released on Zenodo, and here is the link. This slide basically shows you a little bit of how challenging the annotation task was. Everything in red might have been a distractor signal that the human annotator had to avoid, which didn't actually inform or pertain to the R0 estimate task. And the other color codes pertain to the properties or the 6 properties that we chose to model. Furthermore, another interesting aspect of this is like some works reported multiple R0 estimates on different populations. So the large language model also had to cluster the relevant units of information together. So that was also an additional part of this information extraction task. Furthermore, we tested 2 different kinds of formats, like data formats. One is the text format and one is the JSON format, to see which one the large language model would respond best to. Of course, the JSON format is highly desirable because that helps with downstream processing, programmatic processing of the output. So what we did at the time was we fine-tuned a moderately large a language model, specifically Flanty 5, that was already known to be instruction-tuned. And we found that it outperformed GPT 3.5, which was like the state-of-the-art GPT model at the time. So, of course, the GPT 3.5 model was known to have 1,000 times more parameters. And here we see the Flanty 5, its significantly smaller model, outperformed transforms it. We also release some qualitative observations of the data where the human can explore like the human annotation versus what the LLM has produced, because sometimes the quantitative evaluations can be an underestimate of what the LLM is actually doing. So basically that's released on the project website. So we basically have, here you see an abstract, and then we juxtapose the human annotation versus the LLM prediction. And then you can toggle through multiple of our data points to see the output. So the reason we did this is oftentimes the LLM is actually producing information that is quite accurate. It's just missing a little bit of a specificity from the human annotation. So this is kind of a way to qualitatively observe the data. So the best fine-tuned model we released on Hugging Face. So now moving on. So now I talked about dashboards over this large-scale structured information. So we went ahead and implemented this as well. So this is what it looks like. So with this dashboard, our objective was streamlining access to scholarly articles and their structured information. Indeed, we have visualization charts implemented as a dashboard operating over structured scholarly contributions. So on the left side of the screen, you see the interface which is the virology dashboard front end. And on the right side of the screen, you see the back end that kind of powers this interface. So on the front end itself, there are like three main components. One is a summary statistics of all the data in the database. Then we have like a traditional list of papers that allows a user to browse the papers. And then we have visual charts that basically allow researchers to filter for articles based on certain research questions that are already programmed within these charts. The backend workflow essentially works like this. So there is a scheduler that on a monthly basis queries PubMed and fetches articles from PubMed, then feeds it into the large language model, which does the additional filtering and structuring for information. That's then fed into the database, and then it goes into the web API, which then serves the data to the different interfaces that are programmed. And this scheduler indeed works on a monthly basis. So we see now with leveraging a large language model, this information can scale quite considerably, and this workflow works automatically quite smoothly. With humans, of course, as part of the loop, but in a curational effort and not necessarily to enter all of the data from the start. So the database at the moment has over 1,000 structured summaries, and we've actually broadened the objective to over 20 infectious diseases, as you can see on the slide. So there's now influenza, hepatitis B, measles, and so on and so forth. So indeed, at the outset, our aim was to use the power of information technology, specifically these charting technologies, to assist researchers within a single dashboard in filtering for scholarly knowledge. So thus each of these interfaces is designed to answer specific research questions and present the information in a visual summary. For instance, the research question 1 or the chart 1 shows you what is the maximum reproduction number reported for any given disease that is recorded in the database. So this basically allows you to very easily click on any of the charts and so on and so forth. So maybe we could just quickly visit the interface. Right, so this is basically a live system. So you could also like kind of like reduce the span of the data. So you're just interested in R0 values in this range. And so when you click on it, if I could just click on it. So now you see the PubMed article. So the researcher wanted to see, okay, that R0 level for this specific disease. And now this article reports it. So then they can basically visit that article on PubMed, to get more information as they're interested. So this is an alternative to like filtering and accessing scholarly article information. All right, so back to the presentation. So yes, I've just collected the references on this slide and moving on. So now I'm going to shift the focus of the talk to how we've applied LLMs around various tasks concerning ontologies. So starting with the empirical evaluation of various large language models for science with respect to the ontology learning task. So this was a work that we published at ISWC last year. So yes, within our research group, we also do, apart from trying to develop practical solutions, we also do basic science research work. So our work for LLMs for OL falls under this umbrella. The motivation for this work at the time was that we see various anecdotal posts on the media claiming LLMs are unfit for science, LLMs are unfit for math, and so on and so forth. So what we did was we selected one of these aspects, and then we decided to empirically measure the fitness of LLMs for a task. So check the fitness of LLMs for science, but now we ground it for a specific task, which is ontology learning. So this basically contributes to the greater objective of understanding how fit LLMs are within scientific domains. So ontology learning itself is the process of like automatically generating ontologies. Right. So it's the process of automatically generating ontologies. Ontologies, as you know, are like they organize conceptual data. So they're like structured conceptual knowledge. So they're where concepts are organized as types and also non-taxonomic relations. So in this work, we tested the following hypothesis. Can LLMs effectively apply their language pattern capturing capability to ontology learning, which involves automatically extracting and structuring knowledge from natural language text? Here we comprehensively tested 8 diverse model families, which were the state of the art last year. And as we know, this field is rapidly changing as time progresses. As new and more LLMs are being introduced. Furthermore, we broke down the task into 3 subtasks. So we identified term typing as one of the essential tasks to ontology learning, then discovering the taxonomic relations and the non-taxonomic relations. So these were the 3 different tasks that we tested for. We also tested ontologies from different domains of knowledge. So now we are interested in like trying to empirically measure the fitness of LLMs for science. So now we are kind of like trying to broadly look across different domains of knowledge. And I'm going to skip some of this detail. Right, so our results were rather mixed. So we see that when the ontology itself has like fairly few concepts, then the LLM performs very well. But for more complex domains like biomedicine and so on, the ontologies, the LLMs were underperforming. So this could also reflect the nature of the task, as well as maybe some generalizations of like the conceptual term names that were used. So I'm going to quickly skip over this. So here as a takeaway message, at the time we found bigger was better. So the bigger the LLM that we applied to the problem, the performance like boosted given the number of parameters in the model. So this is basically links to the paper. So at this year's ISWC, we also organized and the LLMs for OL challenge. I know you will be there, Ricardo. So we are very happy to present the findings of the challenge because we have participants from all over the world who submitted systems, and some more recent methods like retrieval augmented generation and so on and so forth have been tested. So it would be very interesting, and I cordially invite you all, if you're going to be at ISWC, to come to the session. As a next task, we then evaluated the fitness of LLMs for science, but now with respect to the ontology matching task. So now the ontology matching task essentially is a central task within this domain that aims in finding correspondence between classes of concepts in 2 different ontologies. So it tries to align different ontologies. So of course it's a well-explored research area, and we came in with like the application of LLMs or LLMs across the board. Of course, there are certain alternative ways of modeling OM using LLMs and making all possible pairs and so on, and feeding the entire ontology to the large language model and so on. But each of these methods have their own limitations. So if you feed entire ontologies, you will often run out of the context, or some of these concepts are not even necessary to be included and might distract the LLM and so on and so forth. So we kind of, instead of doing that, we used retrievers. So the retrievers act as a first step to filter out all of the most obvious, like concept classes that even shouldn't be paired in the first place or given to the LLM. So we kind of then leverage the LLM to do the hard work, which is then identify the pairs that are actually worth matching. So the components were, first of all, we had to find a representation for the concepts. Then we implemented a retrieval model, and then followed by an LLM, and finally did some post-processing. So in terms of concept representations, we found in these ontologies that the concepts, not all concepts had descriptions, because often this is very informative to disambiguate a concept to the large language model. So as an alternative, what we did was we used some of these hierarchical relationships to help disambiguate or ground that particular concept to the LLM. So we used the concept representation, concept parent, and concept children representations. So we use 4 different retriever models, 8 LLMs. This is more recent work, so you see some more recent LLMs on the screen. So these are some of the prompt templates that we use for the LLMs themselves. So that's what the concept representation looks like, the concept parent and concept child. And essentially, it was a binary classification task. Just answer yes or no whether they match. All right. Again, here we tested ontology pairs from different domains of scientific knowledge. So there's biodiversity, there's material science, there's phenotypical knowledge, and so on and so forth. So within the results analysis itself, we first tested the impact of the retriever models to recall the correct pairs of concepts that should be matched. So that's what we tested as a first results analysis. So that's basically what's presented in the slide. And just in the interest of time, I would refer you to the paper for more details, or we can also chat about it in the breaks. So as a second step, we then tested how the LLM did in the actual matching task. Here we saw that the concept parent representation of the concepts was highly effective for the LLM to perform better in matching. And note that this is a very generic framework, so none of these LLMs have been customized to any of these domains. So much of the prior work actually is based on custom solutions. So that's just going to skip. So that's basically an essence of how we applied LLMs for a different task around ontology construction, specifically ontology matching. And finally, and more recently, we are also using LLMs in evaluation objectives. So this is where the tools that we use to generate knowledge, we are actually using in turn to also understand knowledge or demonstrate their understanding of knowledge. So we are kind of like using them to kind of reflect on what they're already doing. So we've started testing this particular dimension on the task of scientific synthesis. So this is a bit of a motivation, right? So they have offered us several benefits so far in streamlining machine learning development, but they also can impact evaluation processes because they reduce the dependency on human-generated ground truth data and the necessity for human evaluators. And this they do in 2 key ways. They can either facilitate the generation of synthetic ground truth data, or they can serve as evaluators for model predictions themselves. So this is basically like 2 ways to look at LLMs within the evaluation scenario. So in this work, this was a short paper that is forthcoming at the Convents Conference, which is kind of like presenting some of our ongoing work. So this is where we use LLMs as evaluators to streamline the evaluation process, specifically for the task of synthesizing scientific abstracts. So this can be seen as a task of multi-document summarization and is quite predominant in several contemporary search engines, for example, AIKG-SD, which is also on the agenda. And I'll quickly visit the platform to show you an example of a synthesis task. So for example, I choose this research question. So what you see here is a synthesized summary of the top 5 papers that address this research question. So in our task, what we try to do is use LLMs to evaluate how good and how meaningful those summaries are. And we started with the definition of 3 different synthesis quality criteria, like comprehensiveness, trustworthy, and utility. And this slide basically just provides an overview of related work that are beginning to use as LLMs as evaluators in various other kinds of tasks. So closer to our work, we found that only one other work investigated the task of text summarization evaluation. And this was applied in the news article or the newswire scenario. Nevertheless, so here is what we've done. So we've kind of, in this work, since it's like kind of a work in progress or a preliminary work, we've kind of compared how LLMs evaluate these scientific syntheses compared to how humans evaluated those scientific syntheses. So from related work, we had a corpus of human annotations for the scientific syntheses. That's how we could compare the two. And we used two LLM evaluators, GPT-4 Turbo and Mistral, and the data set essentially was the core GPT data set. So this is what our prompt looks like. Here you see the prompt instruction, then you basically see some specification of the rating scale, and then we describe the rating criteria as well. So here you see some example outputs. So we see that GPT-4 was better able to adhere to the prompt instruction than Mistral because you see it's generated some text that it was not asked to generate. We've actually tried to discuss qualitatively how the human evaluations compared with the LLM evaluations. And our results did show that the LLM models were indeed quite worthy contenders to the human evaluators for a task of this complexity. This is a correlation slide. Right. So as a conclusion to this particular ongoing work, we've seen both LLMs rationale occasionally contained inaccuracies or flaws, raising concerns about the credibility of the score, which kind of points to a little bit of an alignment needed to large language models to essentially understand the task or comprehend the task very well. Furthermore, the extent to which the responses are evaluated as syntheses and not answers also remains unclear. So these were certain open questions that were left in our work. So with this, I'm slowly coming towards the end of my talk. And of course, I'm really happy to chat with you about any of these works or even your own. And I would like to acknowledge the following projects. First of all, the Open Research Knowledge Graph project, and then my own research group, SciNext. With this, I thank you for your attention, and I'm happy to take questions.